So today I want to talk to you about gold nanoparticles as cancer assassins. And to get us in the spirit of things, here's this very scary looking group of folks from Assassin's Creed. Okay, anyway, so what's special about nano gold and what would make it a good cancer assassin? Well, there's a couple of things. One, the melting point of bulk gold is 1064 degrees Celsius, which is high. But if you remember from a previous lecture, when you shrink down the size, especially of metal nanoparticles, the melting point will drop. So 5 nanometer gold particles have melting points of 600 degrees C, which is significantly lower. Another thing is that gold forms bonds with amine and thiol groups. Now, if you don't know what that means, here's little pictures of some amine groups down here, and here's a thiol group. Basically, an amine group is a nitrogen with some free electrons and some groups bound to it, and then a thiol group is a sulfur bound to a hydrogen, and then it's some other group over here that then binds. Now, gold forms bonds with these, which allows those gold nanoparticles to be tagged with ligands. Ligands are molecules which attach preferentially to the outside of the nanoparticles and then bind preferentially to molecules or receptors on tumor cells. So, first of all, exploiting the difference in melting points, the observed difference in melting points has led to the manufacture of gold nanoparticles coated with specific molecules designed to attach to the cancer cells. Then the gold-loaded cancerous cells are targeted using a low-power laser light, which heats the gold and destroys the cells. And one advantage of this technique is that only the cancer cells receive the largest gold loading. The surrounding cells with much lower loading are less affected by the treatment. And so here on the left in the figure, we see the growth of human prostate cancer tumors in mice. And this is from a publication by Stern and colleagues. And what you see here is in the white, you see the control group. In the darkest color here, you see a group that was treated with lasers without gold nanoshells. And then in the kind of medium gray here, that is a group of cancer cells, tumor cells, that were treated with gold nanoshells plus a laser. And you can see that even after just 1 week of treatment, those cancer cells, that tumor was shrunk and completely almost obliterated to zero within the noise of the volume of the tumor. And what's more, the tumor didn't really seem to come back after a time. So this has been shown in studies to be an effective way to target the tumors and kill them, using this lower melting point of gold and heating the gold nanoparticles that are in the tumors. Now, the laser's light wavelength can be chosen to match the absorbance of the gold nanoparticles due to the surface plasmon resonance, which increases the efficiency of the laser's heating. So if you take the wavelength of your laser and make it match the wavelength of the surface plasmon resonance, then you're getting the highest efficiency of energy transferred to those gold nanoparticles and hence the tumor by heat. If you remember, the surface plasmon resonance from an earlier lecture was the excitation of the electrons on the surface of the gold nanoparticle in sort of a wave throughout. Okay, so it was the excitation of all the conduction electrons within that nanoparticle. Now, why would the gold nanoparticles preferentially go to the tumor sites? That was kind of glossed over in some of the discussion earlier. Well, that's due to something called the enhanced permeability and retention effect, or the EPR effect for short. The EPR effect is the property by which molecules of certain sizes, like liposomes, nanoparticles, and macromolecular drugs, they tend to accumulate in tumor tissue much more than they do in normal tissues. Why? Well, the general explanation given is that in order for the tumor cells to grow quickly, they have to stimulate the production of blood vessels. So they need a lot of blood to feed them if they're going to grow that rapidly. So some cancers express signal proteins like VEGF and other growth factors that stimulate angiogenesis. Angiogenesis is the technical name for the growth of new blood vessels. So you can see here in this series of images, up top you see normal blood vessels and normal vasculature, and then underneath you see the kind of vasculature that you might see around a tumor cell. And you can see that it looks very different. There seems to be a lot more of these blood vessels there feeding that tumor cell. and that's the EPR effect. Now, using the EPR effect to deliver little nanoparticle bombs to tumors is known as passive targeting. Active targeting is when you use a ligand bound to your nanoparticle that binds to a receptor that then occurs preferentially on the cancer cells, on the tumor cells. So it's passive targeting if you use the accumulation of the nanoparticles in the tumor due to the increased vasculature and the increased feeding of the tumor cells. That's passive targeting. Now these tumor cell aggregates start to become dependent on that blood supply carried out by these new blood vessels for their nutritional and oxygen supply. Now these newly formed tumor vessels are usually abnormal in form and architecture, okay? They were grown kind of sloppily, so they leak a lot. And furthermore, the tumor tissues lack effective drainage, and all of these factors lead to abnormal molecular and fluid transport dynamics. And that leads to the aggregation of these little particles in the tumors and not as much in the healthy tissue. You can see in this little cartoon here, you can see these macromolecules, or you could envision them as nanoparticles as well, kind of moving through the bloodstream. And because the normal tissue isn't very leaky, they can't get through there. However, they can get through to the side where the malignant tissue is, or the cancerous tissue. They can get in there, and then they can aggregate and accumulate. And so this is being exploited. This EPR effect is being exploited to passively target tumors. Now, speaking of active targeting, here we go. So cetuximab, learning to pronounce that word. It's a mouse and human antibody. It's used to treat several cancers currently, and it's administered intravenously. Cetuximab is an epidermal growth factor receptor inhibitor, or EGFR inhibitor. Now, EGFR is a protein that's overexpressed in many types of cancer cells. As the name suggests, EGFR stimulates further growth of the cancer. Cetuximab bonds to the EGFR with a higher affinity than the natural ligands bind to the EGFR. And so what happens is the drug inhibits growth and induces apoptosis, or cell death. And studies have shown that gold nanoparticles bound covalently to cetuximab, which then binds to the EGFR, improves the performance compared to the drug alone. All right. So here's some little cartoons. The cetuximab is the generic name. One of the companies that makes it calls it Erbitux. I think I'm saying that right. And then here's their little diagram of the cetuximab binding to the EGFR there. So now another idea for using gold nanoparticles to kill cancer is using gold nanoparticles as radiosensitizers. Okay, so what's that? Well, you probably know that radiation therapy, or radiotherapy, is one of the most common treatments for cancer. It uses high energy particles or waves like X-rays, gamma rays, electron beams, or protons to destroy or damage cancer cells. Now, high Z materials, or high molecular atomic weight materials like gold absorb radiation, high energy radiation, more strongly than the body's soft tissue. So here you see a plot. Gold is in the solid curve and the soft tissue is in the dashed curve. And you can see what's plotted is absorption versus photon energy. So the energies that would be given, for example, if you had light that had wavelengths of these energies, 10 to the minus 1 MeVs is about 12 picometers, and 10 to the minus 3 MeVs is about 1.2 nanometers. So you're in the X-ray to gamma ray region here that you might use for targeted radiation therapy. So since the gold absorbs the radiation more effectively, then you could improve the efficiency of the radiotherapy if you move your gold nanoparticles to the site of the tumor. And then you would have that gold nanoparticle sitting next to your tumor because they tend to agglomerate there, right, due to the EPR effect. And you could also attach ligands to the top of your gold nanoparticle that would specifically bind to receptors that are present in higher concentrations in tumor cells, right? So you can make those gold nanoparticles attached to your tumor cell and then hit them with radiation. The gold nanoparticles would then absorb the radiation more efficiently than the surrounding tissue. And then they would have sort of a cascade effect because it would emit photoelectrons and other things as you target that gold nanoparticle. It absorbs the energy, and then due to energy conservation, it's going to have to re-radiate that in multiple forms, Auger electrons, all kinds of things. And then those would be, since it's right next to the tumor cell, absorbed by the tumor cell. So this would improve the efficiency of the radiotherapy. And I'm going to quote here from an abstract that's studying radiosensitizing effect of gold nanoparticles. A major problem in the treatment of head and neck cancer today is the resistance of tumors to traditional radiation therapy, which results in 40% local failure despite aggressive treatment. The main objective of this study was to develop a technique which will overcome tumor radioresistance by increasing the radiation absorbed in the tumor using cetamixad targeted gold nanoparticles in clinically relevant energies and radiation dosage. In addition, we have investigated the biological mechanisms underlying tumor shrinkage and the in vivo toxicity of gold nanoparticles. The results showed that targeted gold nanoparticles enhanced the radiation effect and had a significant impact on tumor growth. The mechanism of radiation enhancement was found to be related to earlier and greater apoptosis, angiogenesis and inhibition, and diminished repair mechanism. Additionally, gold nanoparticles have been proven to be safe as no evidence of toxicity has been observed. So you can see here, it caused greater apoptosis or cell death. It reduced the angiogenesis, right, which is the development of the new blood vessels, and it diminished their repair mechanism. Okay, so these gold nanoparticles have been shown in vivo studies, which means with live subjects, to reduce tumors and help kill cancer. All right, so that's 3 ways that you can use gold nanoparticles as cancer killers. So hopefully this will be one of our arsenal in the fight against cancer in the years to come. Thanks for your attention, and I'll see you later.